Hello, my name is Liliana Velasquez-Montoya. I am an assistant professor at the U.S. Naval Academy, and in the right you see the name of my collaborators from NC State. In this presentation, I am going to first begin with a brief introduction on the relevance of tidal inlets and the description of Oregon Inlet, which is the particular inlet that we have been investigating. Secondly, I will describe the findings on the morphodynamics of the inlet obtained from observations and numerical modeling, and I will finish discussing some of the potential threats that changes in the inlet can cause on coastal infrastructure, specifically to a coastal highway. So with that, I'm turning off my face here. And I'm going to begin by saying that tidal inlets provide many benefits to local and regional economies because they are strategic locations for navigation, commerce, and tourism, and they provide access to ports, harbor, and in general regions that are protected from the action of the open ocean. But with those benefits, there are also challenges related to the morphological evolution that occur in timescales that range from a few days up to centuries, and spatial scales that range from tens of meters to kilometers. So, understanding the physical processes that govern the behavior of these systems is important for sustainable sediment management plans and also for the management of infrastructure in these complex and dynamic environments. So what better place to study tidal inlets than the Outer Banks of North Carolina? This is a barrier island chain that separates the Atlantic Ocean from the Albemarle-Palmico Sound. In the Outer Banks, the tides are semidiurnal with a range of 1 meter in the ocean side and 30 centimeters in the sound side. And the waves are seasonal. During the summer, calm conditions prevail with the occasional occurrence of tropical storms, while during the winter, more energetic conditions take place as a result of extratropical storms. Oregon Inlet per se has remained open for 170 years, and it has always been wider than 600 meters. South of the inlet is P Island, where a terminal groin was built to protect the southern abutment of the bridge that crosses the inlet from the migrating channel in this system. On the other side, the Body Island sandspit is accreting due to the littoral drift that in this area moves sediments from north to south. The main channel of the inlet is leaning towards the southern side of the system with a maximum depth of 16 meters. As mentioned before, there is a bridge across the inlet, and this bridge is part of the NC-12 highway. This roadway constitutes the main terrestrial access to the barrier islands south of Oregon Inlet, and it is the main evacuation route for people that live south of Oregon Inlet. So as you can see, there are many natural and man-made features happening at this place. And our aims are to increase the understanding of the medium-term morphology in tidal inlets in general, but also particularly in Oregon Inlet, by means of geospatial analysis of remotely sensed data and hydrographic surveys, and also by using a morphological numerical model. We also want to relate the morphological evolution of these tidal inlet systems to potential infrastructure vulnerability with emphasis on transportation corridors. Now, I'm going to explain what we have learned so far about the decadal morphodynamics of Oregon Inlet from observations and numerical modeling. We analyzed time series of wave conditions and aerial imagery going back to 2005 until 2015. From aerial imagery, we were able to digitize geospatial metrics of inlet evolution that allow us to identify evolutional trends of the system. So we trace shorelines, speed area, minimum width of the inlet, and channel orientation. And in this slide, you can see the first plot shows a time series of minimum width of the inlet in white squares and a speed area in black circles. We see that these variables have an opposite behavior before Hurricane Irene, which occurred in 2011. The speed area was at a maximum, but during that hurricane, the speed actually breached, and by the end of 2015, it had not gone back to pre-Irene values. By looking at the white squares, you can see that the inlet was at one of its narrowest points before Hurricane Irene, but after that, it had become wider, reaching about 1,000 meters in width. Now, this time series show the direction of the main channel of the inlet, and the linear trend indicates that the main channel has been rotating about 13 degrees towards the north in a counterclockwise direction. While analyzing aerial images, we also identified that at certain points in time, there was sand accumulation in the inlet side of the terminal groin, in this area shown here in pink. And this third plot is showing significant wave height and direction by colors, and in red dashed lines, the times when those sand waves were seen in the photos. You can also see that the sand accumulation in the southern shoulder of the inlet has become more recurrent over time and does not display a seasonal behavior. What we found is that the sand accumulation is actually a response of sand waves moving from south to north into the inlet in a reversal of the littoral drift, and this phenomenon can be explained by more and more triangular geometry of the southern ebb delta, where waves refract and sediment is transported towards the inlet. Now, to understand the three-dimensional changes in this system, a morphological model based on Delft 3D and SWAN was set up. This model has cell sizes in the order of 15 meters in the center of the inlet. It has a spatial distribution of sediment sizes, and it also includes a schematization for bridge piles and the terminal groin. For the sake of brevity, in this presentation, I'm not showing details on the calibration or validation of the model, but you can find that information on the papers shown in this slide. Overall, the model was found to be capable of reproducing the general erosion and sedimentation patterns for the inlet. Thus, it was applied to simulate 2 years of natural changes at this system. So in this slide, you can see an initial bathymetry for the inlet, with one main channel heading towards the northeast in the ocean side and 3 main channels in the sound side. After 1 year of the simulation, that was only forced by natural processes, the northern speed tends to grow and fill the northernmost channel in the flood delta. Sand accumulation is also seen in the southern side of the inlet, and the main channel still heads towards the northeast, and a secondary channel begins to form in the ebb delta. In the sound side, the 2 southernmost channels begin to become more dominant. By the second year of this simulation, forced only with natural processes, the main channel of the inlet rotates towards the north, and in the flood delta, the 2 southernmost channels prevail as dominant, and in the northern shoulder of the inlet, a shoal begins to detach, moving towards the sound. So what we learned from observations and the numerical modeling is that the main channel of the inlet is displaying a counterclockwise rotation with a pivotal point around the deepest part of the inlet, and this is a response to the growth of the northern speed towards the southeast, the fixed southern shoulder of the inlet, and the sand accumulation in that southern shoulder. As a response of that rotation, then the southernmost flow channels tend to become predominant in the system. So now I'm going to briefly contextualize how these morphological changes in the system can pose potential threats to NC12 transportation corridor. So as the southernmost channels tend to become more dominant in the flood delta, the estuarine shoreline in the north end of P Island is showing several signs of erosion, which in turn results to less distance between the highway and the sound side. The 3 images on the right show the eroding shoreline at variable stages of erosion, visible at sites A, B, and C, which are all along the convex edge of the southernmost flood channel of this inlet. In that regard, we have looked at shoreline changes in the area using, again, aerial imagery. And you can see on the image on the left that the oldest shorelines appear in green and the most recent shorelines in red. Similarly, we looked at the edge of the flood channel visible from aerial images, which is shown on the right side image, again with older channel edges in green and most recent channel edges on red. You can see that both images and the plots in the center indicate that the shoreline erosion rates and channel migration rates can exceed 4 meters per year with an average rate of about 3 meters per year, which is very significant considering that the transportation corridor behind the marsh is anywhere between 15 to 80 meters from the shoreline. So, ongoing research funded by the North Carolina Department of Transportation is now targeting assessment of the vulnerability of the transportation corridor from the sound side driven by storms and inlet processes. As part of that research, field deployments are underway to gather morphodynamic data in the southernmost flood delta. And the numerical model is also being applied to further explore the processes driving the erosion at this shoreline and for the development of fragility curves. And with that, I conclude with this brief summary. The counterclockwise rotation of the inlet is caused by the growth of the speed southwards and the accumulation of sand in the inlet side of the terminal groin. The southernmost channel has been encroaching into the back barrier at an average rate of 3 meters per year. This is happening in the south side of Oregon Inlet in Pea Island, and current research is focused on modeling and measuring morphodynamics to evaluate sound side and inlet related processes that drive bank erosion, that is narrowing the island, degrading marshes, and increasing the vulnerability of a coastal highway to flooding events. Thank you very much.